So, hello everybody, let's start. My name is Andrei. I am concealer of the academician from ECO. So he is not the dean of the chemistry department, but scientific supervisor. Yeah. So about Moscow State University, just basic things. Moscow State University, the oldest and the biggest university in Russia. So chemistry department is one of the biggest department in the Moscow State University, and all of you right now in the radiochemistry division. So together with Rosatom, we from 2019 we provide in winter school on radiochemistry. So right now it's in the field of radiopharmaceutical chemistry, and now we want to provide you little tests. Please take it.
Вот получается сейчас. Ну, получается, сейчас делать перерыв, да, может быть, перерывать, чтобы понять.
В смысле раньше?
У вас уже по программе. Ну, тем более. Да, сейчас расскажу вообще. Да, 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 да. Мгм. Мгм.
Если я начну говорить, обед,
Можем так. Можем по химфакту навести.
но с другой стороны, не знаю, может, я прочитал больше. Нет, наоборот, 55 слайдов. Так что
Ну, давай так. Нет, в принципе, смотри, сегодня я могу точно их, во-первых, перед тем, как перевести на обед, и сводить, показать, что холл, там, это вообще проблема.
окей, хорошо. Ну, я тебе тогда напишу, как я
Ты
завтра.
сегодня что-то уходить зайдешь?
Нет, у нас такие... Ну, Владимир Ильич, как обычно, я, конечно, всегда знаю, что в эфире происходит вот эти чудеса. Вот, но времени вообще нет.
Пока покой. Вот, понял.
Я бы, если 2 недели вообще иметь время на сон.
Что это значит?
Ну, когда мы говорим сдача отчета Владимира Игнатьевича, мы подразумеваем, что там задействованы все и много влияет. Сегодня, ну, то есть вчера она прилетела, сегодня она придет.
Да. Я хочет.
Это беспредельно, она уже полезно. Не спина. Скажи, ничего для порога.
Что ты? Серьезно? Машу кризис на времени. Да ладно, бесходит погребать. Okay, thank you very much.
Yeah.
Да ничего нет вообще. А какие грибы?
Откуда я знаю? Это какой военный аэродром? Какой аккуратно собирайте грибы.
Какие? Смотрю, какие грибы, погребли, сходил в военный аэродром, он привез нас на... Thank you, sir. Спасибо. Все. If you have some questions, you can ask us. No problem. Все.
Ответственный грибоед. Ну, знаешь, что уже очень давно.
Это вообще ума. За следующим сезоном. Да, скажи, Степан Николаевич съел, и теперь он где-то на колени.
Металл в себе будет. И никаких больше. Давайте, наверное, сначала должен был страховать свою жизнь, и у него теперь нет возможности такого.
Нет. Thank you, sir. Так, все, почти. Владимир Геннадьевич, вопрос. Да, ну, thank you, sir. Я поэтому тебя и позвал. Я говорю, ты еще там хоть написал, или как-то вопрос задавать.
Самое главное, есть. Когда можно ответить, он рассказывает, что он запускался, вводит все.
Ну, спасибо.
И говорит, вот, значит, не дает ему картиночки, и потом выделяете ресурсы, ну, у кого наибольшая радиоактивность в картинке, мне кажется, тот и победил. Вот. Ну, соответственно, там тем, в том числе, регулируют и мхи. Вот, потому что они абсорбируют на себя небольшие, там, все дела, ну, правда, концентрируется все самое тяжелое. И в целом нет ничего удивительного, если там найдется тяжелый металл, потому что это главное, их можно ногами поставить, но с точки зрения радиоактивных металлов. Но ситуация очень интересная. Я такой люди, нужно Степана, слушай, там Лукашов коллектор по Армении. Придет, он там привез, знаете, у него жена боится. Вот. Ты можешь померить там. Ну, главное, вы не спать, ну да, на шее.
Это очень удобно искать. Спасибо.
Очень удобно.
Ну, спасибо.
Ты задаешь вопрос больше. Лучше идти.
Да. Спасибо. So thank you very much. Just a few issues about organizing issues about this day. So from 12:45 we have a lunch break. Yulia will take you to the main building of chemistry department, and in the evening, I think about 6:30 p.m. We have dinner in the restaurant, so near the radiochemistry division. Hope that we'll go with you together with Yulia, maybe without you. So today we have three lectures, and first lecture will be from Peter Matveyev, yeah, and it's about basics of ionizing interaction with matter and its application in nuclear medicine. So let's start.
Let's start.
Wi-Fi password here, you can find it on the board.
Так, мне презентацию в интернет отправлять, да? Ну, в смысле, демонстрацию экрана делать? Ну, да. Ну, это просто под запись, там никто у нас не сидит. Все ребята сидят.
Ну, они в YouTube будут сидеть.
Хорошо.
Hello, everyone. As I understand, most of you is it Russian speaking? Yeah. So let's consider our school like a very good English practice. For me, it's I think the first time when I give a lecture on English. So I believe my English will be understandable for you and also for me. So our first lecture will be about basics of ionizing interaction with matter and some examples how we use its features of ionizing interaction with in nuclear medicine. I really believe that you're familiar with this picture. So it's how we can protect ourselves from different types of radiation in case of external radiation. And this is three types. First is alpha radiation, and it's easily stopped by 5 or 10 centimeters of air. We can also use a paper to stop it. In case of beta radiation, it's better to use light elements such as aluminum or different kinds of plastics. And also in case of beta radiation, it's a really bad idea to use lead protection because during interaction of electrons with heavy metals, heavy materials, its product Bremsstrahlung radiation. We will talk about later what it is. And in case of gamma or X-rays, heavy metals is the only way to stop it or reduce it to very low levels. So brief description of this type of radiation. First one is the heavy charged particles, especially alpha particles. Some features. First feature, so alpha particles is really heavy. They double charge. They have strike tracks when it goes through the matter. And I think the important place here that it was two types of ionization. First one is a direct interaction with matter of alpha particles. And after this interaction, we obtained so-called delta electrons that have enough energy to continue ionization of matter. And the biggest part, the most part of ionization is produced by d electrons, not by primary interaction. And there's one value that used to describe the loss of energy during pass in matter. It's called linear energy transfer. And it's interesting that the highest lead is occurred in the end of the path in matter. And if we try to look at flux of the alpha particles, we also can note that during the path, during the traveling through the matter, the flux is a constant, and it significantly decreases only in the end of parts or of the path. So why it happens? Because for any interaction with matter, we need a time. And when alpha particle or heavy particle go through the matter, its velocity goes down, 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 and in the end of the path, the velocity is so low that it's possible to make lots of interaction with matter. And because of this, the maximum lead is observed in the end of the path. And this feature, this effect, can be very useful in case of proton therapy, because we can use accelerator to accelerate protons, for example, and by varying of energy, we can vary the lengths where the maximum lead is observed. And if we compare this interaction with photons, with gamma radiation, external gamma radiation, we can also know that in case of photons, the highest dose is observed in the very end of the wave of photons. So, and in contrary, in case of protons, as I say, we can choose conditions where we can observe so-called break peak. This is a break curve in general. And we can find the depths where there is a tumor, and the biggest part of the dose will be observed in these depths. So, and some kind of imaging of dose in case of irradiation by X-ray or gamma and protons, and as we can see, in case of X-ray, the dose spread in all of, for example, head, and in case of protons, the main part, I think at least half of the living tissues are not suffered from additional dose, and we can find the biggest part of the dose in the tumor. In case of electrons, these particles is lighter than alpha particles, and because they are one minus charged, and because of it, the distance in different kinds of matter is higher than in case of alpha particles. Here you can see the effect distance in centimeters in different materials. It's also dependent on energy of electrons, but compared with alpha particles, they're really higher. And as I say, Bremsstrahlung effect, in case when charged particles change its trajectory, and when it goes near the nuclear, because of electrostatic interaction, of course, it will change its trajectory. Every time when trajectory is changed, we can say that this particle is accelerated. And in case of charged particle is accelerates in some kind of field, it should give some electromagnet ionization emission. So because with the higher charge of nuclear, their yield of such kind of interaction is higher. So that's why it's impossible to use heavy metals to protect ourselves from a different kind of electrons. So also another specific feature of interaction of electrons with the matter is Cherenkov-Vavilov radiation. It looks like some blue light. You, I think, already see it in case of nuclear reactors, and in case of spent nuclear fuel put in in the water, for example. This effect is observed when the speed of electrons is higher than phase speed of light. And how we can calculate phase speed of light by dividing speed of light in vacuum on a refractive index. And in case of water, in case of electrons, the energy is, I think, a bit is low. And for usual battery emitters, the energy of electrons is much higher than this value. So because of it, in case of electrons, this effect is easily observed. So also, when we're talking about electrons, it's important to note that the main part of interaction with matter is a scattering. You can see it here. And this is how we can estimate the part of electrons that will scatter in the matter. And also, in case of electrons, we also should consider positrons. There are many positron emitter radionuclides, and they are very useful in case of nuclear diagnostics in nuclear medicine. So after it emits positron, of course, it has some energy, and when it loses its energy, it fires an electron, and after that, process of annihilation occurs. The pair of electron and positron disappears, and we obtain two annihilation photons that fly away with angle about 180 degrees. The energy of this photon is fixed. This energy is conducted with the mass of electron and positron. And the last type of radiation is gamma radiation. Gamma quants have no charge and have no mass. It has three mechanisms of interaction with matter. And first one is photoelectric effect, when all of the energy of gamma quant goes to the electron. Second one, and after such kind of interaction, there are some processes considering of reconstruction of electron shells. And also here we can see so-called Auger electron emission. It's also important mechanism, also important way of decay in case of some radionuclides that used in nuclear medicine. Also, another mechanism is Compton scattering. It looks like similar with the photoelectric effect, but the energy of gamma quant, it goes partly in electron and partly for another gamma quant. So it looks like incomplete photoelectric effect. And the third mechanism is electron-positron pair production. It looks like anti-annihilation process. So in the contrary of annihilation, it's where the energy becomes some matter. So from one gamma quant, we obtain a pair of electron and positron. They fly away from each other. The main criteria for this kind of mechanism, that energy of gamma quant should be higher than two energy equivalent of masses of electron and positron. And about penetration ability of gamma radiation compared with alpha and beta particles, it has the highest penetration ability. In some way, we can consider the ability of stopping like an exponent dependence on the thing of matter. And this is how it works when we're talking about three types of decays in case of external radiation, and what will be gone where if we put it inside of the body. Alpha and beta particles completely absorbed into the human body, and this type of decays is used for therapy. And in case of different types of gamma quants or annihilation photons, this way is used for diagnostics. As any part of medicine, nuclear medicine, as I say, can be divided in two parts. First one is the diagnostics, next one is a therapy. In case of diagnostics, we use radioactive substance and the way of its decay for identification of structural and functional changes in organism or in organs or even in tissues. In some cases, we can observe these changes even at the level of cells. And the use of such kind of diagnostics in some ways can increases the chance of recovery and also saves money on treatment. In case of therapy, the main idea is that we targetedly irradiate some kind of organs or tissues and absorb those, allowing the death of tissues or even single cells. And we try to minimize damage the living cells, living tissues, or the so-called normal tissues. So nuclear medicine, I think it have history about in its history about dozens of years, and this is the first, at least the first photography of studies of thyroid gland using iodine 131, and this is modern 3D visualization with using combination of positron emission tomography and computer tomography. And here we can see the main places where tumors is occur. So here you can see some main features of radioscope diagnostics. So I think when we compare radioscope diagnostics with any other types of diagnostics, for example, computer tomography and so on, one of the main feature, one of the main pros of it is the visualization, and we can observe some changes in real time. All of another techniques, it's impossible for them to make some observation. And the last point here is when we make a target radiopharmaceuticals that can go specifically to the some of tissues or even single cells. So here's is the list of main methods for medical imaging. First 4 types of them, it's non-nuclear medicine methods, and this is a list of some for the techniques that use internal radiation. First one is the planar scintigraphy. This is the easiest, I think, type of diagnostics here. Then 2 types is SPECT, single photon emission computer tomography. The second one is a positron emission tomography. And here there's a combination of computed X-ray tomography with these 2 types of nuclear medicine techniques, and the best way is to combine them. I think for now nobody use these techniques without computer tomography, And also the last one is a combination of positron emission tomography with magnetic resonance imaging. And as I say, this is techniques can show metabolism and functional changes in the organism. So about tomography, the main idea is a combination of cross-section of organism that gives you 3D visualization of the organism. So for this technique, there was the Nobel Prize was given, but the main disadvantages of this technique is the relative high dose for organism. Just a reminder that per year, people in the Earth obtained about 2 millisieverts. And in case of this procedure, I think this range is higher because sometimes even 50 millisieverts can be obtained by one procedure. Planar scintigraphy. Mainly this technique is used for diagnostics of kidneys. In these techniques use, I think, one of the simplest radiopharmaceuticals based on technetium-99m, iodine, indium, and so on. In general, they used without any additional organic ligands. So this is SPECT. We obtained, we put into organism gamma radioisotope, and we used two detectors, two scintillation detectors, as presented here, to register gamma emission, and after that we can understand where it's mainly occurs in the organism and give some ideas about placing of tumors in organism. So this is, I think, in case of SPECT, the most popular radionuclide is technetium-99m. It used in some as a combination, as a stable complex with different organic organic that are technogenic, for example, technetium chelates, but sometimes it's used with some of biological molecules, such as albumin, such as peptides, and so on. In case of positron emission tomography, here radionuclide that goes positron decay. If we consider this radionuclide map, the positron emitting radionuclides, they have not enough nitrons to stabilize the nuclear. And because of it, nuclear goes through beta plus decay. And here you can see, I think, the main important radionuclides for PET. I think the fluorine 18 is the most popular radionuclide. You will also have a lecture about positron emission tomography, as I understand, in Friday. This is typical scheme of PET center. In the first floor, there is a cyclotron that used for production of fluorine. Next floor is a radiochemistry part when fluorine is halides by some organic ligands, some organic molecules, and after that, in the next floor, it puts on in the man, and we've got scanning in PET. Also, once more time, in case of PET and SPECT, we use to compare its computer tomography because in case of every positron emission radionuclide, as I say, positron have energy to go from the place where it decays, and because of it, there is some uncertain in diagnostics, the place where was the decay. And only with combining with computer tomography, we can understand where, in what tissue there was a decay. So it's also, there are some requirements for radionuclides for diagnostics. Their gamma radiation should have enough energy to go through the body, but this energy shouldn't be high as possible, because high energy of gamma radiation will produce a more dose that that is not preferable for diagnostics for irradiation of man. So this is the second tip here. Also, the half-life time for radionuclides should be enough to conduct the procedure, but after the procedure is over, we should the radionuclide should decay, and when we have short half-life time, it's also will make the dose that go to the man lower. And in case of positron emission tomography, in one hand there is high yield of beta plus decay, and also at the same for gamma radiation, the energy of positrons should be as low as possible to make this distance shorter. And in case of radiotherapy, yes, it looks like, I believe that you remember this game. I think now it's not so popular as it was. So we use charged particles to destroy tumors. First, so we can use corpuscular, is alpha particles, beta particles, sometimes neutrons and protons, and also we can use electron magnetic emissions, X-ray radiation, gamma radiation. So in case of radiotherapy, we can observe three types of such kind of therapy. Is external beam radiation therapy, is called stellar therapy. So also when source of radiation in contact with the body, but it's not in the blood of patient, it's called brachytherapy. And when we put radionuclide in the body, it's called radionuclide therapy. So here are some figures. This figure is about external beam radiation therapy when we use so-called gamma knife form, and all of this gamma rays is focused on the tissue. And this is example of work of radionuclide therapy. This figure is before radionuclide therapy. This figure is after of radiotherapy, and we can see that there is lower parts in black. This is after PET scan, and black places is where was the tumor, and here we can see that part of tumor is significantly lower. So for radionuclide therapy, we can use three types of particles. First one is the Auger electrons, alpha and beta particles, and they have really different range of interaction. Auger is really low; it's about 10 nanometers. Then is alpha, about 50 to 80 micrometers, and in case of beta radiation, it's quite between first two types of radiation. And when we try to compare X-ray. For example, if we destroy the DNA of injured cell, in case of X-ray, there's even no interaction. It's a really low interaction between X-ray with DNA molecule. And in case of heavy ion tracks, in many cases, it destroys the DNA molecule. And if we want to, when we want targetedly put radionuclide in the organism, we should make some radiopharmaceuticals that will go targetedly to the tissue. And here we also should note that radiation therapy and X-ray diagnostics, everything that connected with external radiation, is not classified as a radiopharmaceutical. As I say, we can put a radionuclide in. We should put radionuclide in the body, and we can use different forms of injection of radionuclides. There are bright view on this. This is, I think, one of the easiest way when we use salt of, for example, radium. I think it's still only the only certified radiopharmaceuticals that use alpha decay radionuclide, and because of closest chemical properties of calcium and radium, radium will go to the bones of patient, and by this we will destroy bone metastasis. Also, when we use ionic forms, for example, iodine 138, it goes targetedly in thyroid, and because this is kind of iodine is a beta emitter, it will destroy the thyroid cancer. Also, you can see the results of I think SPECT, and after that you can see that there is a lot of radionuclide, and after we destroy thyroid cancer, there is I think 0 of radionuclides here. Another way how we can put radionuclides is some kind of complexes between radionuclides with some small molecules such as chelators. Here you can see example of complex between samarium and some kind of phosphate containing halide. And also because of high affinity of phosphates with the bones, this is also used for therapy, also therapy of some kind of metastasis. And here you can see the results of such kind of therapy. Here also small such so-called small molecules. It's fluorine desoxyglucose (FDG), and this molecule, it was called a molecule of millennia because after it was used for diagnostics in nuclear medicine, there was, I think, an explosion in case of diagnostics in the first stages of cancer. And because of the use of this molecule, many people didn't die from cancer. And about this molecule, I think even a single lecture will be given. And another example of, I think, ionic form of radionuclides is rubidium 82. That used for some diagnostics in heart. But the main disadvantages of FDG, because of high metabolism of glucose in the brain, it's impossible to use it for cancer, brain for diagnostics of brain cancer, and in this case, even a series of molecules that can go to the brain is used. It's quite complex molecule compare with FDG, and it's used for sometimes for brain cancer, sometimes in Parkinson's diseases, and in general, when we're talking about radionuclides, it should have three parts. First part is a radionuclide that give us diagnostics or therapy effect, and it also has a so-called biological vector that delivers this radionuclide to the target organ or target tissue. But sometimes it's impossible to connect a radionuclide with a biological vector directly, and we should use chelator that will complex the radionuclide, and it also be possible to connect it with a biological vector. And when, for example, in this case, is this octreotide use that conjunct with the surface receptor, and because of it, radionuclide comes in really closeness with the cell surface. What can be used for biological vectors is strongly depend of type of cancer, in type of tissues and tumors. Sometimes, as a last example, there can be peptides. Sometimes more complex substances as antibodies that will connect with antigens in the surface of cells. And also sometimes there are really difficult combination of different organic complexes and biological complexes is used. As I say, if we destroy the DNA of injured cell, it will die. But it's really difficult to put the radionuclide directly near the DNA. As you can see here, they're a bit easier to put radionuclide near the cell. But of course, the efficiency of this type of therapy will be lower than when the radionuclide goes closer to the DNA molecule. And what benefits it gives? Here you can see the living of different cells, for example, glioblastoma and adenoma of humor carcinoma. And you can see what goes on when we use free radionuclide. We can see the death of cells, but if we use such kind of biological models, the deaths go even with very low radioactivity, and it goes much significantly higher. Also, there are some more pronounced example when, in case of ionic form of iodine, there is even no therapy effect because it easily conjugate with serum albumin in blood. And when we use it in a modular transporter, we can observe high rate of dying of cancer cells. And also about contact of radionuclides, brachytherapy now is widely used. But the main difference from radiopharmaceuticals, we put the radionuclide into the body in different ways, for example, by needles, but there is no contact of radionuclide with the blood. And here two lists of radionuclides that use in diagnostics and for diagnostics and for therapy. They're part of PET radionuclides, part of SPECT radionuclides, and some radionuclides for therapy. Some of them are still not used. They are very promising, but there is no radiopharmaceuticals that was certified in some countries, except based on radium. And also, it will be very convenient when we can make a procedure when we also have a therapy and we also have diagnostics. For some radionuclides, it's possible, and this way is called theranostics, with addition of part of these two words. But the list of radionuclides, of course, is shorter than in the first two cases. And considering the ligands that combine biological vector with radionuclide, of course, there are some list of requirements as for radionuclides that we can use in nuclear medicine. First of all, it's a quantitative bonding of the radionuclide. It's a quite difficult task because when we put it into the organism, some interaction with different metals that occur in blood, with some different biological molecules that can also conjunct this metal. The interaction, the halates should go in at room temperature, because in case of many biological vectors, when we try to speed up the interaction of radionuclide with chelator, it's impossible to use high temperature because biological vector can be destroyed. And because we use different kinds of radionuclides, most of them had short half-life time, and it's important to this interaction between complex formation should go as quickly as possible to not to lose the radionuclide. And the process of obtaining new radiopharmaceuticals, it should go with many specialists, or with chemists, biologists, and of course medics. And because we need to produce radionuclides, there also should be physicists. And that's all. Any question? Okay. I think now we have lots of time before lunch. As Andrei told me, you will have an excursion in chemical department, but it needs a short of time to prepare it. And now I think you can go to the coffee and tea. Thank you for attention.
Just like this. Every day. Yes, every day. That's good. We don't need to. Guys, هو ده السيرفر هو أساسي. هو دي بتاعته بس هو رسالة الأمريكية قال لك هتلاقي بس مكتوب بس here. Actually, very,
كده هو الاسم اللي يكتب بطريقة تانية في ال
اللي كبص الانجليزي
بتاع بقى.
اللي كبص الانجليزي
فكرني ممكن عشان يكتبوا.
No, no, no. وتقريبا خلصنا لو ده اللي عايز اللي عايز يعمل حاجه يعملها الساعه 9 دقيقة هنا في الجوع تشتغل ممكن تشتغل راحه أو تقريبا الاثنين صح هو
There's a notebook. There's a notebook. You can use the type C. There's a laptop. You connect to the laptop. How often can you open it?
break
Breaker.
break
Breaker?
forgot.
No, I don't.
You don't have it.
No. What is this?
This is card for transport.
No, I don't. It will be cheaper there if I buy it.
I don't know, but I think it. But you put money in this card and you will. Because every day we will take 2 bus.
Yes, maybe 100 rubles, yes.
No, 2 bus maybe.
The 55 rubles.
23 and 23.
No, yesterday I paid.
No.
55, yes, 55, yes, 51. This I asked Professor, I can go to
No, but not, principle.
how much?
This one spent. This one.
Yeah, how much will you try to manage?
Yes, that.
Where we can get this one? How much it cost?
Because I made it with, very for
We need this. 10 years, 10 years to use.
Today, we must take. Understand. I will be here on the 4 days. No, we will be there.
Yes, yes,
You can't bring us. You don't drink or just.
Drink? Ah. Ah. Oh,
There is no good smoke. There is no human in life without. Yes.
smoke.
Yes. But that's not mistake, it's a truth. Everyone has a big.
You use it to, you cannot, you use it to smoke. Yes. It's difficult. But you don't smoke difficult. Oh, yes.
Maybe. It's shaped like five and. Maybe it's actually for I don't know. What? It must have the different places. That one. Right, this one is 20. 22. This is how long. Again, just put next
Let's go to 1 year old. Good year. 25.
Yes,
Professor, Professor,
what do you think?
I said 24. 25.
39. It's a nice. But I will keep with my. But everybody I guess in 29. Literally, I think. So, I don't want to be different. And there is example.
That's what should do some research. We should some research paper. I think it's for those. Also, we should also have one. Also, we are going from paper.
We finish a topic with a paper.
Each section has its.
Yes, that is not going to be.
Oh, I understand.
It's just like that, then I use.
That's why the master is. I'm thinking about all data because I study paper study. If I study it, if I get higher score, how, for example, 50% will be percentage discount. Yes, three.
It's like, maybe, yes, I told you.
Something else. Молочников, explores world.
Yes, also, maybe,
Don't work with this example. Only don't forget. One, yes, on-code is made of this things why. Yes, on school. No, we choose because nuclear reasons. All the 6 why are people, engineering. Again, automation, yes, I'm mechanical because it's time interest.
Now,
Because it's smart. I started this at dynamics.
it's
Something not study.
How you get it?
Lower.
Lower and
Maybe 5.
I get it, like,
Right? Exam and also. I get mixed in.
I can say like.
Until the exam, you can take 100 times. But this is. You have gaming experience. But what's the
Там расписание по их уже входило. Ага. Потому что они там 20 лекций. Ага. Ну, понятно.
Your second year. You are second year.
stay there.
What? No, I started touching. I'm from Tergana. What? Tergana. Tergana? 2 hours from Tashkent. What is the name of Saturday? What? Saturday. 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 What time? Saturday. Vidro. Vidro. Saturday. Vidro. It's a shellac. Yes. Shellac. Shellac. Saturday. Vidro. Это vidro. Это shellac. In Uzbek language. No, shellac. Atar. That's atar.
You have a.
Yes, no.
We need it to have.
No, accent. It's accent. What's the same? They speak it out easily. For example, you and you.
It's the same, for example, in Spain. Actually, Spain is quite, we can say small one, but they have a lot of classes. I mean, in different regions. There is some regions in which they speak so fast, like English, very fast.
Yes, I think I saw
No,
Indian word excellent language. For example, if you study, if you look people, for example, if you want to examine the first master speaker, every university has an example of Indian and Pakistan outside us. Because no English exam. Because English very excellent India without phrases. They speak very fast. English that's the right.
That's your right.
Right, I think what this
Like you check.
no, in Latin. Philippines,
Chinese, like.
Singapore is really
Yes, sign, official, going to official. Yes, I
Please. You can. How you can job opportunity? What? Job opportunity. Job opportunity. What's happening?
Не очень дал. Читать, перебирать.
Yeah. We will have a short excursion. I think we will see on the bottom of our department. We will show you radiometric room and one room with our Röntgen laboratory spectrometer. So you need to divide it into two groups. Do it now, please. Okay, yes, let's wait. One of the group goes with Tatiana and one group goes with me. Everyone is ready. Hey.
Ой, вот она с обратно вернули. Она же собрала. Ой, надо не было что.
Ну, мне не выслушайся себя приходит, поэтому они не тормозят. Ну, жить целого дня, ну, у нас нет она потом подошла, потому что нам сказала.
Может, не надо. Она такая, нет, не надо. И потом она, и все. Я теперь занималась. Как бы, не очень проявительно, если честно.
Она такая, ой, да, расстроились. Так, расстроились? Девушки там так старались.
Я заходжу в коридор, там будет
Ну, мы потом
Что для этого нужно?
Да все, в зуме просто у нас трансляция запущена, поэтому я сейчас перекопирую на нашу частоту. Где-то 50%. Да.
See you tomorrow.
Сейчас 15, да? А еще будет какое-то видео, да? Или нет?
Нет, нет, просто демонстрация экрана.
Хорошо, значит, вот здесь стоит. Нет.
Какой первый?
Запись 2.
Да.
Окей, давай проверим один такой. Работает у меня. Есть. Помнится.
Good afternoon, dear colleagues. I am Rami Zaliyev. I work in National Research Center for Chemical Institute in Moscow. I'm head of laboratory of radionuclides and radiopharmaceuticals. My duty is to develop new methods of production of radionuclides, mostly for medical applications. Today we will speak about nuclear reactions and mostly applications of nuclear reactions to radionuclides production. Generally for nuclear, for biomedical or medical applications. Here you can see the nuclear chart. I think you already know that here you can see stability line, and from right side of the stability line, a number of beta minus emitting nuclides, and here you can see nuclides that decay by positron emission or by capture of orbital electron. And most of radionuclides from this right side can be produced in a nuclear reactor because they have great excess of neutrons in the nucleus. And therefore, the main method of production of these radionuclides is addition of neutron into a nucleus and using the nuclear reactor. And most of these nuclides can be used in medicine as therapeutic beta emitters because they decay by beta minus mode. And from this side, you can see radionuclides that decay by emitting of positrons, and therefore they can be used. Some of them can be used for positron emission tomography, and also a number of these radionuclides may be used as gamma ray emitters because they decay by electron capture and have no additional particle radiation during decay. And most of this red group can be produced by accelerators of charged particles, for instance, by cyclotrons. And here you can see a small group of alpha emitters that can be also used for medical applications, but most of them can be produced usually by nuclear reactors, but in some cases, accelerators methods are also possible. Here you can see the part of this nuclide chart, and during beta minus decay, you can see that the nuclide shifted this side, and during beta positron decay or electron capture shifted this side. If you can see to the periodic, if you take a look to periodic table, you can see that during beta minus decay, you obtain the next element, and beta plus or electron capture the previous one. Here you can see that our element is transformed during alpha decay. Usually we use such decay schemes for a representation of process of radioactive decay. Here you can see the different states, different energetic states of proton nuclide, and here is the parent one. Sometimes you can see that several methods of decays are also possible. For instance, for potassium-40, but sometimes you can also see 3 or maybe 4 different decay modes. There are a number of data sets that might be used for obtaining of decay data, and I prefer this one. This is a database of Lund University from Sweden, and as for me, this one is maybe most convenient because you can easily find element, or you can make search by radiation or by decay time. It's a very useful one, but it's not maybe sometimes data are not correct because this database is not updated frequently. The first nuclear reaction was done by Ernest Rutherford by irradiating of compounds of nitrogen with alpha particles. Alpha particles here obtained, of course, from radioisotopic alpha source, maybe radium or polonium, I don't remember exactly. And he observed that during this process, some kind of new radiation arises, some sort of new particle with relatively high range, more than alpha particle, and he decided that this type of particle is nucleus of hydrogen, the name is proton, and here is the short form of representation of nuclear reaction. Here is the target nucleus. This is the result of reaction. This is projectile and outgoing particle. This is the same. This is short form of nuclear reaction. The next major step was done by Irene and Frédéric Joliot-Curie, French researchers. They made first reaction of production of completely new artificial radionuclide. This was phosphorus 30. they radiated aluminum foil by alpha particle, and they obtained a new product with very short half-life, and using some chemical experiments, they proved that this is really phosphorus and nothing else. And here you can see the short form of this reaction, and they received a Nobel Prize for this major achievement. And here is some kind of definition of nuclear reaction, but as for me, it's not so easy to make to give definition of this process. I take this definition from Russian handbook of physics, and according to this definition, nuclear reaction is a process that occur when nuclei or elementary particle collides with other nuclei, and as a result of this collision, some properties of this system change. New particle may appear, and some energetical changes also may occur during this process. There are many different types of nuclear reactions. There is no any comprehensive classification of nuclear reactions as for me, but we can separate some special kinds of nuclear reactions. We can see them here. Maybe one of the most important are the reactions by influence of ions, for instance, by protons, alpha particles, helium-3, deuterons, and other charged particles, light ions. And this is a classical method of radioisotope production. Other very important group of nuclear reactions is capture of neutrons. This kind of reactions occur during radiation by thermal neutrons in nuclear reactions, for nuclear reactor, for instance. And several other important types, for instance, fission of heavy nuclei, for instance, fission of uranium, or fission of plutonium or thorium or other heavier elements. This fission may result to different types of fission products. And some other kind of reactions, for instance, fusion reactions, they occur, for instance, in stars, and provide us by energy. And other type of reactions are reactions induced for high energy gamma rays. These are photonuclear reactions, and electrons, accelerated electrons also may induce nuclear reactions, and you can see here electronuclear reactions. And inelastic scattering also is type of nuclear reactions, for instance, by influence of neutrons and protons, or gamma rays. I think that there may be other types of nuclear reactions that are not involved in this classification. Here you can see how target nucleus transformed during the nuclear reaction. Here you can see the results of PN reaction. It means that projectile is a proton, and outgoing particle is neutron. And here you can see alpha-induced reaction, alpha n, alpha 2n, alpha 3n, and so here maybe alpha 4n, etc. And here is a neutron capture and gamma reaction. The same result may be obtained by DE reaction, and so it's also important. In some cases, you can replace reactor methods by accelerator induced reactions. For instance, you can replace N gamma route by DE method sometimes. And here you can see many other methods of producing radioactive products. The most important value characterizing nuclear reaction is cross-section. Cross-section is a quantitative measure of probability of nuclear reaction, and this is a probability that a system of two particles will transform from one state to another one. And this cross-section sigma has a dimension of area because, as you can see, the area is high. Its probability of reaction is more is high. This cross-section is measured in barns. One barn is very small area. It approximately is like a real cross-section of nucleus of medium mass, and here is equations which introduce this value of sigma. You can see that this N2 is a number of products of products of the reaction. Sigma is the cross section, and 1 is a number of nuclei in a target, and this theta is flux density particles per square centimeter per second, and T is irradiation time. You can see that if we have this flux density is higher, of course the number of interaction will be proportional. The same is for the number of target nuclei and irradiation time. It's very easy. We have in nuclear physics, we have several important conservation laws, and of course we have to take in consideration these laws in nuclear reactions. First one is law of conservation of charge. Second one is conservation of number of nucleons, and the third one is energy conservation. Next one, conservation of momentum, and conservation of angular momentum. Of course, during nuclear reactions, because we obtain some new products, this process may be with sometimes maybe endothermic or exothermic. And for endothermic reaction, this reaction only can occur if the energy of incident particle is greater than the threshold energy. Threshold energy is very close to the Q value. Q value is the energy of the reaction, and energetic effect of the reaction. but usually this threshold energy is a little bit higher because part of energy of incident particle converted to the kinetic energy of the compound nucleus, and so therefore, because of law of conservation of molecule. Here is the connection between threshold energy and Q value and masses of the projectile and the energetic effect of nuclear reactions may be easily calculated using very famous Einstein formula. This is the mass defect difference between masses of products of the reaction and reagents, and this is proportional coefficient that connects the energy and mass. This one units of Q value is MeV, and in this case, this mass difference will be expressed in orbits and units of mass. It's very easy. You can find these values in databases, and usually sometimes it's possible to usually it's possible to replace masses of nuclei by two masses of atoms, because the number of electrons is constant during this nuclear process. There are several important mechanisms of nuclear reaction, and maybe one of the most important was suggested by Niels Bohr, and this is a most important mechanism for medium energies of incident particles, from approximately to up to approximately 100 eV. And Bohr suggested that these reactions goes through formation of intermediate product compound nucleus, and then this compound nucleus decomposes to other products. Lifetime of compound nucleus is very short. You can see it here. It's very short, but in any case, this is much more than needed for nucleon to pass the distance equivalent to the diameter of nucleus. But if we have high energy of this bombarding particle, for instance, if it is close maybe to 1 giga-electron volt or something like that, in this case, some direct processes can occur without formation of this intermediate product. Usually, nuclear reaction can proceed by different ways or different channels. You can see then, for instance, if we radiate or bismuth by alpha particle, we can obtain astatine 212 and 1 neutron. This is alpha N channel. And also at the same time, you can obtain another isotopes of astatine, and also, for instance, 2, 3 of neutrons. And also it is possible to obtain polonium isotopes and 1 proton and several neutrons. This means that we can obtain mixture of different products during nuclear reactions, even we have a constant energy of bombardment particle. And if we have a relatively low energy of irradiating particle, a reaction goes according to Niels Bohr, it goes via formation of intermediate product. And you can see that in this example, this intermediate product may be obtained by two different methods, by radiation of gallium with protons or by radiation of zinc with alpha particles. And both these reactions go via this intermediate product, and therefore we can expect the same distribution of reaction products after decay of this compound nucleus. And really, if we analyze the data from databases for cross section of these two reactions, this is for first one and this is for second one, you can see that they are really very similar, not completely, but similar. You can see that this is a cross section of for germanium, and this is for other isotopes, and you can see that these two pictures are very similar one to another. And this may be considered as proof of concept of compound nucleus. And this is just one example. You can see a number of such cases. We know that atomic nucleus is a quantum object, and therefore it can exist only in several energetic levels. It's not possible to obtain something between these levels. And sometimes nuclear reactions can go through some of levels of this compound nucleus. But if energy is very high, in these high energies, we cannot separate distinct energetic levels of this compound nucleus, and therefore no any quantum effects observed during these processes. For instance, if we use low energy of alpha particles, for instance, if we radiate boron 10 by alpha particle, we can see that there are several energetic levels of compound nucleus nitrogen. And if this reaction goes, for instance, via this first level, we have the peak of cross-section, peak of probability of this reaction because of resonance process. If this energy is exactly fits to the difference between these levels. Here is the second resonance that corresponds to the second level of this third one, and you can find a number of these resonance peaks in excitation function. But it is important only for process with relatively low energy of bombarding particles, and therefore these resonances can be seen only with reactions with light nuclei because of high Coulomb barrier for nuclei from the middle part of periodic table, for instance. And all of these methods may be used, for instance, for determination of small amounts of boron, for instance, in semiconductors. And you can not only measure amount of boron, but also distribution, surface distribution in upper layer of semiconductor. For this purpose, you have to measure to determine these protons. For instance, this line, P0, may be measured. Here you can see the spectrum of protons outcoming from boron during this reaction. Also, you can measure by measurement of number of these protons, you can obtain the number of boron atoms in material, for instance, in silicon, for instance. Yes. Was the scheme of setup of experiment. Here is the target, beam and detector for measurement of these photons. For instance, these methods is a nuclear reaction analysis, very useful in material science. Another important example of resonance process is the burning of helium in stars. Because to obtain something more heavy than helium during nuclear synthesis, 3 alpha particles should collide for carbon, for nucleus of carbon. This is not very it's a really improbable process, but it's possible only by passing this resonance level in carbon-12, and here is the level of alpha particles plus two alpha particles connected in unstable beryllium 8 quasi nucleus. We cannot find this nucleus in nature or produced by some methods, but it's not really stable. But through this relatively low difference between these levels, we can obtain all material in our universe that is more heavy than helium. But these resonance processes are important, for instance, for astrophysics or material science, but for neutron-induced reactions. But in most processes that we conduct in accelerators, we use relatively high energy particles, and in this case, we obtain this intermediate product with relatively high energy of excitation, and in this case we use evaporation model to describe the processes in this nucleus. And in this model, the energy that is transferred to the nucleus, then redistributed between nucleons in this nucleus, and if energy of any nucleon exceeds the binding energy, this nucleon can escape the nucleus. If we have still the excess of energy, the second particle can be emitted, and the third one, and so on. And the residual energy is emitted usually as a gamma ray. When we perform reactions with charged particles, it is necessary to take into account the Coulomb barrier. This is some energetic barrier between nucleus and bombarded particle, because they have the same positive charge, and therefore the repulsion between these nucleus and particle takes place. Here you can see the schematic representation of this Coulomb barrier. And this barrier is also important if you have some reactions with proton escape from nucleus, for instance, or alpha particle escape. And during escape, this particle also should overcome this common barrier. Sometimes it's possible to pass through the barrier because of some quantum effects. That's also possible, but it's not so probable. The example of this passing through barrier is alpha decay, because, for instance, for uranium or other heavy nuclei. The most important characteristic of nuclear reaction is excitation function. This is a function of dependence of cross-section from energy of particle. And here you can see two different cases. First one is for exothermic reaction, and second one is for endothermic reaction. For example, induced by charged particles. In any case, you can see that in relatively low energies, we have small values of cross-section. This is due to this Coulomb barrier. But for endothermic reaction, this excitation function starts from threshold energy that is very close to the Q value of the reaction. Here is a complete form of this excitation functions, and you can see that this is the typical ones for proton-induced reactions. This is experimental data for irradiation of tellurium-125. You can see that at the lowest energy we can see the PN reactions because there is the lowest threshold of this reaction, and this is a most important is in relatively low energies. Approximately, we need about 10 MeV to for removing one neutron from this intermediate nucleus. You can see that this maximum of this excitation function is about approximately maybe 12 MeV, and then next process will predominate because probability of escape of two neutrons from nucleus is higher than escape of only one, and in approximately 20 MeV we have maximum of P2N cross section, then P3N, P4N, and other ones. Here you can see only PXN reactions. Also, we have some reactions with escape of protons, of alpha particles, or something else. This is just a picture for PX reactions. For neutrons, we have a completely different picture because neutrons are neutral particles. They have no charge, and therefore they have no any Coulomb barrier, and nuclear reactions may occur with from the lowest energies of neutron. The most important process in low energies is the radiation capture, is the capture of neutron by nucleus. And this cross-section of this process increases with decreasing energy as 1 divided to velocity of Newton, because we have no column by. But in this case, we also have a number of resonances, most of them located in between approximately 0.5 electron volts to 1 keV. In this region, we have a lot of sharp peaks on excitation functions, and these are due to resonance effects. Cross-section for radiative capture sometimes may be extremely large. In some cases, we have cross sections as big as 1 million of barns sometimes. For fast neutron, we have approximately cross section approximately close to a real cross section of nucleus, approximately close to maybe 1 bar or something like that. This is a theoretical modeling of excitation function of thermal capture of neutrons by Rosatom 176, and here is the thermal region. This is epithermal region with a number of resonances, and this is a fast neutron region. The next important group of nuclear reactions is the reactions induced by energetic photons. We will discuss them in more details in our next lecture. Here you can see how these gamma rays may be obtained, but usually they are obtained by interaction of accelerated electrons with heavy with target made from any heavy material, for instance from tungsten or platinum or something else, and these electrons may be transformed to gamma rays with high energy. And by influence of these gamma rays, we can perform such kind of reactions as gamma N, gamma 2N, gamma P, and other types of gamma-induced nuclear reactions. Here you can see the typical spectrum of gamma rays obtained from accelerated electron beam. This is the energy of electron. Also, this is the maximum energy of continuous spectrum of gamma rays. And this is a typical cross-section excitation function for instance, for gamma P reaction or I think 68. This was obtained by theoretical modeling. When we plan to produce some sort of nuclei, some radionuclides, we have to make choice between several ways of production. Usually we have different types of nuclear reactions that may result in our product. For instance, this radionuclide, this is a schematical representation in nuclide chart, may be produced, for instance, from PM or D2M or alpha P3 reaction from this one, or alpha PN from this one, and also by neutron capture or DP reaction from this nucleus. Sometimes we have a number of possibilities. Have to make a selection between these different methods. Our first step when we have to make such choice is the analysis of data, of existing data of experiments. And for instance, you can find so-called X4 database. This is a database of experimental of nuclear experiments. There are several different portals that provide access to this database. This is our site from Moscow State University. As for me, this is the most convenient way. You also can find this database in IAEA, for instance, website, or another also in another websites. Here you can specify your target, your bombarding particle, and result of nuclear reaction, and you can find all experiments that are known, that were done, and results that were published concerns this nuclear reaction. And you can find, for instance, cross-section of these processes. For instance, this is for production of gallium isotopes by irradiation of zinc with zinc 68 with protons. Here is a cross-section for gallium 67. This is for gallium 66 and gallium 68. And you also can find this data also in a numerical formal table, and also you can find references to all original articles. This is very convenient for data analysis. And this is only one aspect of production of radionuclide. This is the nuclear aspect. You can choose some nuclear reactions that can lead to your result. And you have taken into account the energy of this bombarding particle, and using this functions, you can calculate yield of product, and also you can calculate the number of byproducts and radioisotope purity of the product. The second important questions that you also have to take into account is the radiochemical aspect of production, because you have to separate your radioisotope from the irradiated target. Day after tomorrow, we will have a special lecture concerning this radiochemical aspects of production of radionuclides. Sometimes this is the real challenge to separate a reaction product from irradiated target. For instance, it's in the case of lanthanides with very similar chemical properties. For instance, when you separate lutetium-177 from irradiated detected targets, it may be really challenging, because the ionic residue of these two elements are very close, and chemical properties are very, very similar. And specific of our work is that you have to obtain your radionuclides with high chemical yield, because process of radiation is very expensive and you cannot waste a lot of products in reactive wastes, for instance. It's will be very expensive. And another problem is that you have perform all your chemical works very fast, because sometimes you deal with radionuclides with really short half-lives. It's not a case of retention. It's about maybe 7 days. It's enough for separation. But for instance, if you deal with, for instance, at the time, 2 hours, 7 hours, it's not too much for chemical separation, and you have to do all your procedures very fast. Another problem is that you have to work with reactive materials. During separation, most of procedures should be organized remotely in order to protect the personnel from radiation. The first important problem that you have to take into account is the production of targets, because, for instance, during the radiation on accelerators, you have a relatively high beam current, and you have, in any case, heating of this target, and a lot of problems with dissipating of this heat from the target. You have to cool the target, for instance, by water from backside, or by helium from the face of this target, or sometimes by both sides. And in any case, it is sometimes real big problem to avoid melting of the targets or burning of the position of this target. When we produce radionuclides by the means of cyclotrons, we use several types of nuclear reactions. Really, the easiest way is application of peer reactions. In this case, you can use protons from relatively low energy, starting from relatively low energy, from maybe approximately from 10 MeV. Usually it is enough for production of radionuclides by this reaction. And in these cases, usually you have no byproducts. It's a relatively clear way of production of radionuclides. But by these methods, you can produce only several radionuclides that are very close to the stability line on the nuclide chart. Here you can see several examples of radionuclides that may be produced on low energy cyclotrons. These are radionuclides for positron emission tomography, short-lived radionuclides, fluorine 18, carbon 11, nitrogen 13, and also several metals that also suitable for positron emission tomography. This is cadmium 44, copper 64, yttrium 86, zirconium 89, and iodine 1, 2, 4. The next group of radionuclides that they are mostly used for gamma ray tomography for SPECT. They usually produced by P2N or P3N reactions, and they can be produced by medium energy cyclotrons. Usually we have such type of cyclotrons we have in one region. For instance, we have in Moscow region such cyclotron, one in our institute, but low energy cyclotrons are relatively cheap, and then they can be located in directly in clinics for production of these short-term radionuclides. The next generation of cyclotrons are cyclotrons with relatively high energy. It's not really high energy in the physical sense. It's really it's a medium energy, and these energies up to 70 MeV may be used for production of several important radionuclides. For instance, production of strontium-84. This is very important radionuclide for generator of rubidium. These generators are very important for cardio PET, for positron emission tomography of Hertz, and several other radionuclides may be used for therapy, copper-67 and scandium-47, and also Tin-117 at stable state. These radionuclides can be produced by P4N reaction for this strontium and P2P reactions for these three radionuclides. Usually, if we use these protons of medium energy, usually we have a mixture of products, because we have a number of open reaction channels, and also P4, P4N, P3, and P2N, Pn, and other channels are possible for this relatively high energy. Here you can see a picture of contemporary new one medical cyclotron for 70 MeV, and this was produced by IBA company from Belgium, and now several cyclotrons of this model are installed in all the world. For instance, in the United States, in similar is in France, I think, in Aranax, and maybe in other countries also. When we use neutrons for radionuclide production, we have several key reactions. First one is neutron capture and gamma reactions. These methods may be used for production of lutetium or for instance, copper 64, but the problem is that this reaction cannot be used for production of radionuclide without carrier, because you obtain the isotope of the same elements that you have in your irradiated target. Irradiated lutetium 176, you obtain the 177, and therefore you have a mixture of two isotopes of lutetium. You cannot obtain this without carrier by this way. Another method of radioisotope production by neutrons is irradiation of heavy nuclei, for instance, of uranium 235, by thermal neutrons. And in this case, you have a number of different fission products, and you can separate some of these fission products from this mixture. This is the most important method of production of molybdenum-99. This radioisotope is material for technetium generators, and this is the maybe most important radionuclide for practical medical application from the point of view of number of medical procedures that made annually in the world. And another important product is iodine-131, but this is not common way of production of this radioisotope. Usually it is obtained by radiation of tellurium. And also it is possible to obtain strontium of this from this radiation, and then this product may be used for construction of generators of yttrium-90 that also may be applied for production of radiopharmaceuticals labeled with yttrium-90. Next type of nuclear reactions that neutron-induced nuclear reactions that may be used for radioisotope productions are NP reactions. In some cases, they may be performed in nuclear reactor, but in nuclear reactor we have relatively low flux of fast neutrons usually, and therefore some other methods of production of fast neutrons may be applied for radionuclide production. Now the several types of accelerators are developed to produce high intensity beams of neutron beams. They based, for instance, on reaction on, for instance, on carbon by the action of theranostics, and they can produce relatively high intensity beams of neutrons that are suitable for radioisotope production. But now it's I don't know any working facilities of when accelerator produced neutron are used for real applications, real medical application for production of radionuclides. The main advantage of N-gamma reaction is that in this case you usually don't need any radiochemical separation. For instance, if you radiate potassium oxide, you obtain the same element, potassium, and you only have to dissolve your irradiated target. You can obtain your product. You need to remove radiochemistry. But the problem is that usually specific activity of the product is relatively low. But in some cases, if you have high cross sections, for instance, several thousands of barns, it is possible to apply this type of reactions for a relatively high amount of radioisotope production with reasonable specific activity. In this case, we have to use some indirect ways for production of radionuclides using nuclear reaction. In order to improve specific radioactivity of our product, we have to use such indirect ways. For instance, we produce beta-emitting radionuclides, that is an intermediate, and after decay, it forms our target radionuclides. For instance, if we irradiate tellurium by thermal neutrons, we can obtain tellurium-134, and after decay of this radioisotope, we can obtain the 1, 3, 4. This is a typical method of production of iodine. This radionuclide is also very important for radiotherapy of cancer. This is a method of production, very cheap method of production of this. Another example is production of scandium-47 by radiation of calcium-46 by neutrons, and then decay of this intermediate product. But this method is not so practical because we have very low abundance of this radioisotope natural mixture of isotopes, and you have to enrich this target, and the cost of this calcium isotopes is extremely high. Don't know exactly, but it should be extremely high. And also next method of indirect production of radionuclides is double neutron capture, then followed by beta minus decay. As example, you can see the irradiation of dysprosium-164 by neutrons, and by double neutron capture, you can obtain dysprosium-166 that then decays to holmium-166. And in this case, you have to separate this holmium from irradiated target. And also you can use other ways for production of non-carrier radionuclides, for instance, NP reactions, but not so practical because we have no such sources of high energy neutrons. And another possibility is to apply fission reactions, but they are suitable only for limited number of radionuclide. The most important example is molybdenum-99. Let's discuss some equations that are important for calculation of radionuclide production. This is a typical case when we have only one product of radiation. This is our target nucleus. This is a result of radionuclide, and we can see that it may decay by beta minus emission, or also can capture neutron and form next isotope. In this case, the rate of formation of nuclei of this radionuclide may be expressed by this equation. First one is the formation by radiation of this nucleus. This second term is decay by beta decay, and third one by neutron capture of by the nucleus of this radionuclide. And in this case, we can obtain several. We can calculate the number of nuclei after radiation for our initial material. It will be given by this equation. For our product of reaction, we can calculate this one by this equation. In this equation, this big lambda letter expressed like sum of two processes of decay and burning of the product in capture of neutrons. In this case, we will have a maximum time of maximum activity when we obtain the maximal activity of our product. When we increase the irradiation time, activity of the product will decrease. Here you can see the simulation results. If it is possible.
Yeah.
Да. Okay. Here you can see the dependence of activity from the irradiation time for three cases. This is formation of lutetium-177 by irradiation of 176. But please please see that the both cross sections are relatively high, extremely high, more than 1,000 for both radionuclides. Therefore, and mass is 1 milligram for in this simulation, and we can see that if we have very high flux of neutrons, this neutrons per square centimeters per second, we will have peak of activity approximately after age 9 days. After this date, we will see the burning of reaction products by because of neutron capture of by this nucleus. And if we will irradiate during 1 month, we obtain nothing. This effect is not so pronounced for relatively low neutron fluxes. You can see that the results activity is relatively proportional to that irradiating time for relatively low neutron fluxes. Okay. I think we can. Okay, we will discuss this case, then make interaction. Here you can see more complex situation with production the same. This is a more complex situation. This is indirect production of the same radionuclides. In this radionuclide, in this case, we start from not from lutetium but from ytterbium isotope, neutron capture of by ytterbium-176, and then beta decay to our resulting nucleus. We can see here. You can see the scheme of production of this lutetium, and in this case, this equation of formation of lutetium will be. You can see here. First term is formation by decay. Second one is beta decay of lutetium, and third one is burning of product because of neutron capture. And in this case, it's also possible to calculate a number of nuclei after irradiation for lutetium. This is a working expression that may be used for practical applications. And the third case is double neutron capture. For instance, this is a nuclear capture or by tungsten 186 and the second capture by 187 and we obtain as a result tungsten 188. Very similar to the previous case, but in this case it is important that we have here we have the term this flux of neutron flux in power 2. That's very important, and therefore you can obtain tungsten 186 only 88 only if you have very high nuclear fluxes in nuclear reactor. Okay, I think I can make this break. We have to second that. So discussion. Ну, давай с этой закончим. Okay, but let's finish with this. Start another one. Here is, you can see comparison of different methods of production of special 177. This is very important radionuclides because now it's very popular, very promising for therapy of different type of cancer. And now it's approved by FDA. Some radiopharmaceuticals with mutation are approved by FDA, and therefore it's very popular, but unfortunately it's not so easy to produce this radionuclide. Here you can see that there are different options. Two of them using neutrons and one using accelerator, deuterons. Here you can see the chart illustrating production of potassium. Here is the direct way, this one, irradiation of potassium 176, and this is indirect one. The problem is that potassium has two isomeric states. This is a ground state. This is useful isotope, and this is admixture. This is a long-lived isomers that sometimes it forms in a small amount, but this small amount can complicate application of potassium in medical purposes. And when you irradiate potassium by neutrons, small amount of isomeric impurity also forms. But when you use indirect way, you have no isomeric impurity. Therefore, this is more comfortable to introduce potassium by prototerbium. But there is a very complicated chemistry of separation of terbium from potassium, and I think we will discuss this more detail day after tomorrow. Also, it's possible to use deuterons. We obtain also possible to obtain potassium with beams with energy up to 15 MeV, beams of deuterons. Also, we have two ways, but for us it's no difference what is the main reaction. The most important is this one, but in any case we have the same product. But relatively low yield of production of potassium, and also the same problems of with separation of potassium from intermediate targets. When we use direct route, we have a very high cross section, and we can obtain relatively high. Due to this high cross section, we can obtain relatively high specific activity. Approximately 25% of nuclides from target converted to the product, and this is, as for me, it is enough for production of target radiopharmaceuticals, and in high flux reactors, it's also possible to obtain 65 curie per milligram. It's extremely high specific activity. The main problem is isomeric impurity because it's not dangerous for patients, but it's complicated handling with these radioactive substance because clinic has to deal with radioactive waste to find methods of utilization of this radioactive waste may be challenging for clinics. By indirect route, also it's possible to produce lutetium, but in this case, cross-section is low, but specific activity is high because we know stable lutetium in our product, and maximal theoretical activity, specific activity that can be obtained is 110 curies per milligram. This for pure lutetium 177. No isomeric impurities we have in this case, and therefore we can use longer use this product. No run wastes up to decay of lutetium 177, and but complicated radiochemistry. Another problem is that we have a highly enriched target, and therefore the material is expensive, and we have to regenerate this expensive material. Here you can see summary of the selection, and you can see it at home. This is a finding of David Taylor's younger alchemist. I use this picture because what we do is some kind of chemistry, and we produce radionuclides, new elements from another one. For instance, once we produced radioactive gold from mercury, it was the most close to a chemical practice. Okay, I will switch.
Надеюсь, я справлюсь на рабочем столе, да? Окей. То закрыть, пожалуйста. Володь, наверное, мне... А может и нет. Оно, просто чтобы оно по экрану пошло, потом по экрану, чтобы оно запустилось по зоне. Запустить я не могу. Уже
Okay, well, next our topic is the production of radionuclides by using photon beams. It's not very popular practice, but it's very promising as many, and I think maybe in the nearest future we will see several facilities of production of radionuclides using photon nuclear reactions. As I already showed you, this is the most important method of production of energetic photons. The first photonuclear reaction was performed in 1934 by Chadwick and Goldhaber. This was a photodissociation of deuterium, because deuterium is very not very stable nucleus. It has very weak connections with of nucleons in this nucleus, and it's relatively easy to decompose this nucleus. Progress. Еще кто-то подключил, да?
Я.
В смысле?
Ну, все, теперь. А?
В смысле даленного из-
Нет, не знаю, что это
А, And for decomposition of this nucleus of deuterium, it is enough to use gamma rays that may be obtained by radioactive decay from thallium 208, and this is a member of natural radioactive series of thorium, and this energy is suitable for decomposition of deuterium. The second experiment was performed by Szilard and Chalmers. And this was for the decomposition of another relatively unstable nucleus, beryllium-9. It can be easily decomposed by, for instance, by neutrons or something else, by alpha particles. And in this case, it was decomposed by gamma quanta. I don't remember exactly what is the slide, but I think this also should be from some natural reactive products. Because in this year, there are no possibilities to obtain gamma rays used, for instance, by accelerators or something like that. And most researchers use natural sources of conductivity, such as radium, polonium, others. Here you can see the chart that represents the processes that may take place during irradiation of nucleus by gamma quanta. After excitation of some of this nucleus after absorption of gamma quanta, we can, in some cases, we can obtain other products if this excitation energy exceeds separation energy of neutron or proton. In this case, we can obtain other nuclides. If this energy is lower than separation energy, we have some kind of fluorescence. It's so-called nuclear resonance fluorescence. Now it's very promising, very important method of analysis, of elemental analysis, for instance, in determination of some nuclear materials, that might be determined by this method. But for our purposes, we use relatively high energy of gamma rays, typically higher than 10 MeV. And here you can see examples of reactions of excitation functions of reactions induced by gamma rays. It's very similar to results that we already have seen for protons. First panel is gamma M reactions with elimination of one, and approximately the same value of peak of peak cross section, approximately 10-15 MeV. That is typical for different type of reactions. It's approximately the elimination of one neutron, and here is the reaction gamma 2M, gamma 3M, and gamma 4M. Not only elimination of neutron. If we will radiate, for instance, uranium by gamma quanta, we can see the fission of uranium, and because of high energy of gamma rays, this fission may occur not for uranium-235, but also for uranium
238, and also for thorium, and also for other heavy nuclei, for instance, for bismuth or lead. Also, we can see some sort of water fission when we use high energy rays. Here you can see distribution of mass distribution of fission products after irradiation of uranium. You can see that the results is different when we use gamma rays of different energy. But this distribution is similar to other types of distributions of fission products, for instance, for distribution of uranium-235 fission products in fission by theranostics. These pictures were taken from a recent comprehensive review, and I recommend you this review for you if you want to more closely contact with this topic. It's very interesting, very comprehensive. Usually we obtain gamma rays by two different methods. First one is most popular and most practically important. This is a transformation of electrons by stopping them in heavy target, for instance, tungsten or platinum, or some other materials. By this way, you can produce gamma rays, but gamma rays with continuous spectrum with the maximal energy that is similar to the energy of this electron beam. But if we need quasi-monochromatic gamma rays, in this case, it is possible to use Compton backscattering using laser rays. In this case, it is possible to obtain quasi-monochromatic photons, but using high energy electron beam. But in this case, the intensity is relatively low. This method usually applied for nuclear physics studies, not for radioisotope production, because of relatively low intensity, and because we have not so much sources of high energy electrons. This is a picture of small racetrack microphone. This is a special type of electron accelerator. It's very compact. Here, it's maybe like maybe this table, not so large. This accelerator was developed in Moscow State University as a department in Institute of Nuclear Physics, such also located in this place. This accelerator can give electrons with maximal energy 55 MeV, but with relatively low intensity. It's maybe suitable only for scientific studies, not for routine production of radionuclides. But we made a lot of different investigations, different studies on this using this accelerator, and I will tell you about this works. When we use gamma rays, we have the same problem that we have in radiation in nuclear reactors. The main problem is that we obtain by gamma N reaction. Most typical reaction is gamma N reaction, symmetric for gamma. And in this case, we have the isotope of the same element that we have in our target. Therefore, specific activity of the product is low. You cannot separate isotopes. Principally, it's possible to separate isotopes, but it's now it is complicated and extremely expensive. Maybe in future it will be possible. I read some new papers, new articles in these researches. For instance, in Switzerland, some attempts were taken to separate isotopes for accelerator for radiation. For instance, radiation of some ion into the reactor. After radiation, it's possible to separate stable components from radioactive, but yield is about several percent, maybe up to 10%, a little bit more, but in many cases very complicated and expensive. Therefore, we look for indirect routes production in order to improve, to enhance specific activity of the products. We can use several types of the reactions, for instance, gamma P, gamma N reaction followed by radioactive decay, but in this case we usually have beta plus decay, not beta minus, like in radiation in reactor, because we obtain neutron deficient nuclei, and therefore this is the main decay mode. Also, we can use gamma P N reactions and other reactions that lead to radioactive products that which can decay to another one. This is one of the typical applications of nuclear reactions, production of copper-67. In this case, we can obtain this product, this radionuclide with relatively high activity. In this case, it is not in case of nuclear reactions. It is not so easy to calculate the yield of nuclear reactions and to express this yield, because it's possible to use different units, and we usually use in our experiments such kind of units, becquerels per microampere per hour, per unit of thickness per gram per square centimeters. We use this unit because we have high penetrating radiation, and therefore we have to take into account thickness of our target, not like radiation, for instance, by photons or by deuterons, because we cannot obtain complete attenuation of this radiation. We cannot use 600 units or something like that. And the yield in this case will depend on spectrum, Strachel spectrum. Strachel is German word. This means stopping of this radiation and stopping of electron and radiating gamma rays. And this is the form of this shape of the spectrum, and this is excitation function, and by this expression we can calculate the yield of reaction. And to compare results of for instance, two scientific groups, we have to express in by the same way and use the same result, same techniques of experiment. For instance, if we use different thickness, for instance, of conductor of this first target that stops electrons, In this way, we will obtain different spectrum of gamma rays. Therefore, it will make some complication in comparison of results of different studies. Several radionuclides may be very important for application of in medicine. I already discussed advantages of lutetium, and another other very interesting radionuclides are copper-67 and scandium-47. They have similar properties. You can see that the mean energy of beta rays, beta particles, is approximately similar to this all radionuclides. This energy is relatively low. It is very important for treatment of cancer because we have a small range of beta particles, and therefore it's possible to use for treatment of small tumor, metastasis, or something like that. Therefore, it's preferable to apply beta emitters with low energy of beta particles. And all these radionuclides also have low energy, relatively low energy gamma lines. It's also is an advantage because we cannot trace the distribution of these radionuclides through the body of patients, and we also can use these radionuclides as theranostic. It means that combining therapy and diagnostics. And but these two radionuclides, copper and scandium, are not so popular as lutetium, and the reason is the difficulties of production of these radionuclides, especially for copper-67. It's really challenging to produce this radionuclide because we have no good reactor methods and no good lack of good accelerator methods of production using charged particles. Here you can see several ways. The most popular one is P2P, but in this case you need protons of relatively high energy, about 70 MeV and more, and also you have a number of impurities, and it's not so easy to use this method. Using of fast neutron also is not a good choice because relatively low yield of this method. Also possible to use alpha particles of protons using alpha P and P alpha reactions, but in both cases we have low yields and low abundance of target isotope, and low abundance means high price and necessity of reprocessing. And in this case, it may be wise to use photonuclear reactions. We studied these methods several years ago. Here are the results of different experimental studies, and we also made several irradiations. Here you can see the yields of products, but it's not so interesting, these values. And several years ago, 3 years ago, we published a paper, published article in the Journal of Analytical Nuclear Chemistry about this method. And now with this method of production of copper-67 becomes maybe most popular method of production of this radionuclide. For instance, one company in the United States reduced this radioisotope by photonuclide method. We also developed separation technique. Here you can see gamma ray spectrum before separated and then after separation. It was relatively easy because now we have a special dedicated solvent material for separation of copper produced by Christian or Chrome. It's easy to separate. And here you can see comparison of different methods of production of copper 67, and you can see that photonuclear method is one of the best methods in production. Results of this first compound. Another example. We already discussed different ways of production with lutetium-177, and we also tried to introduce new method. And we decided to study the nuclear production of lutetium by radiation of couple isotopes. In our experiments, we used natural mixture of isotopes, but also it is possible to use some enriched isotopes. As for me, the most suitable is this one. The reaction product is lutetium-177. The method, the reaction is gamma. The problem is that the nuclear reactions with elimination of proton usually have a low cross section because of Coulomb barrier. Because for escaping of proton, it should overcome this barrier, and this is extremely important for nuclei with high atomic number. For instance, lutetium and others. And therefore, this method was not so suitable for production of this of lutetium. These are the result of modeling. This is the shape of gamma ray spectrum from accelerator, and this is the cross section of this reaction. Here you can see the gamma spectra. This is before separation. We have a number of hafnium isotopes and also lutetium, and this is the spectrum after separation. Experimental yields are presented here, and here is our article about this method, but unfortunately the yield is not enough for practical application. Even we will have even we will review it 10 days of huge target of site. It is not possible to produce at least one therapeutic dose of lutetium. Therefore, it's not, as for me, it's not enough for practical application, but it may be useful, for instance, for preclinical experiments, for distribution studies, and something like that. Third case that we can discuss today is production schedule. Here you can see the same problems that for copper 67. We have no good methods for production of this scandium. The only one is maybe P2N reaction on calcium 48. but the problem is the extremely low abundance of this radionuclide. Therefore, it's not the method of choice. Other possibilities are to irradiate titanium by protons of medium energy using P2P channel, the same as for copper. But also we have a number of byproducts, and the chemical radioisotope purity is not good. In this case, good option looks irradiation by gamma quanta of titanium 48 because high abundance of this isotope natural mixture and relatively high cross-section for this reaction because of low atomic number of scattering. This is modeled cross-section for this reaction, and here you can see the experimental yields that we obtained on non-titanium target from natural isotopic composition. In this case, yield was relatively high under experimental conditions. There are several other radionuclides that may be affected by nuclear reactions, and we also made some experiments for to estimate capability of this production method. Here you can see three different types of radioisotopes: two isotopes of polonium and one radioisotope of thulium. All these isotopes may be considered as therapeutical or theranostic radionuclides due to emission of beta particles or G electrons for these two radionuclides. Here you can see the fragment part of nuclear chart, and here are the methods of production of holmium, but in this case the yield is extremely low due to relatively low abundance of this isotope, and in this case we may expect a higher yield than for this one due to abundance of helium. The alternative route of production of holmium is irradiation of dysprosium by neutrons using double capture of neutrons, but in this case you have to use high flux reactor. So maybe 1, 2, or 3 available options with the world. So easy to do. Other possibility is to irradiate to direct production by irradiation of holmium by neutrons in reactor, but in this case you will obtain radioisotope with stable carrier that is not good for medical application. You can use this product, for instance, for treatment of bone metastasis, for instance, but it is not suitable for labeling antibodies or due to low specific activity. Here you can see the yields of erbium and holmium isotopes that we obtained in radiation of neutral erbium oxide by gamma 1. Relatively low yield, unfortunately, relatively low yield of holmium. The same reason, the high atomic number of holmium prevents escaping of proton during decay of this integrated product. The next case that we considered in our laboratory is the production of thulium. Thulium is very interesting radionuclide because it emits electrons, electrons with very low energy, and the range of these electrons is extremely low. For in some cases, it should be about several nanometers. It's close to dimensions of DNA molecule, DNA galaxy cells, and therefore the linear energy transfer is highest for these electrons, and they are very promising for therapy. But if you can provide targeted delivery nucleus of cells, in this case it will work. And there are many ways for production of thulium, and several ways are good, suitable. For instance, irradiation of erbium isotopes by protons is the typical methods, but in many cases we also study the possibility of nuclear production. The main, as for me, the main route is indirect one, gamma N reaction with followed by time plus decay of products. Unfortunately, yield of thulium is relatively low, as in case with other earth elements. Here you can see the spectrum of radiated target. Here you can see thulium isotopes and erbium isotopes, and we also tried to make chemical separation of these radionuclides. It is possible to separate thulium from erbium, but not so easy, but it's possible. And results of this study are also published 1 year ago. As we decided, it's mainly useful for production of small amount of thulium, for instance, for preclinical studies or for various studies. Another interesting example is production of isomeric state of platinum, platinum 195 metastable. It's very interesting radionuclide, but extremely difficult to produce this radionuclide. There are no suitable targets for production of platinum. As you can see, all nuclei that may be used for irradiation by protons or by alpha, they are unstable, and we cannot use any suitable material for irradiation. And the only possibility is irradiation of osmium 192 by alpha particles using alpha N reaction, but this is not so good because typically for alpha N reactions we have extremely low cross sections due to the same problems due to Coulomb repulsion between alpha particle nucleus. therefore this method is not practical production. Other possibility is irradiation of iridium by neutrons in reactor, and by double capture of neutrons, and then decay of iridium 195 to platinum. But it's also in this case we also need a high fluxes of neutrons. It's really not so easy to make this way practical. And we studied another possibility, radiation of gold by alpha particles and by gamma NP reaction to produce these radioisotopes. And it's not so, yield is not so high, but it's comparable with other methods, and we can. It's possible to obtain relatively high amounts suitable for studies. Here you can see the summary of our experiments that were performed on this small accelerator using gamma quanta of continuous spectral gamma quanta with a maximum energy of 55 MeV, and you can see that it's possible to produce a number of radionuclides. As for me, most promising one is this one, scandium 47, and the other interesting possibility is action of copper 67. These are most interesting candidates for the nuclear production. Another possibility is that now discussed in nuclear community is production of actinium fire. This isotope of actinium was very interesting for many years. It attracts attention of medics and biologists and chemists because of unique properties of this radionuclides. Because actinium has relatively short half-life, about 10 days, it's suitable for medical application. It emits several alpha particles, about I think it's 4 alpha particles during several stages of decay, and it's very interesting possibility for treatment of cancer because alpha particles have a very short range in biological tissue, about maybe 50 micrometers or something like that. It's comparable with dimensions of maybe 3-5 cells. And also alpha particles have high energy, about from 6 up to 9 MeV. It's really very high energy and also high linear energy transfer. It makes very interesting possibility to use alpha particles as therapeutic agents, but now it's not yet used in common practice. We have only several clinical studies, but the results are very, very interesting. And several methods suggested for production of actinium-25 using both reactors and accelerators of protons, for instance, accelerators of medium energy protons. Also in Russia, we made several experiments on proton beams. Maybe tomorrow we will have a lecture of Zhukov Boris, I think you know. And for several years we worked together with him, and our task was development of method of production of actinium by irradiation of thorium with medium energy protons about 120 MeV. They have in Troyes, it's near Moscow. They have power facility and intensive beam of these protons that is suitable for production of radionuclide in industrial scale, and we also try to produce actinium. But the problem of proton wave is that if you use high energy or medium energy protons, in any case you have a number of open reaction channels, and you have mixture of radionuclides, and together with actinium-225 you also will obtain actinium-227, that is a long-lived alpha emitter that is not good in medical application, of course. Therefore, some other methods were tested for actinium production, and maybe most popular now, most popular idea is to irradiate radium with high energy gammas in order to obtain radium-225 with high cross section, because for gamma and reactions you have the highest cross section in reactions, and this radium after several days, I don't remember exactly, 15 days, it decays to actinium-225. It's really interesting because it's possible to produce really high amounts of high purity actinium-225. But the only problem is that it's not so easy to work with radioactive heavy with actinium. With these methods, you should use grams of radium. It's very demanding in point of view of radiation safety, because a lot of radon emanates from radium, and it is difficult to reprocess this target to obtain again to obtain a new material for radiation after the procession. It's difficult to produce metallic radium if you want to use metallic nuggets, but a number of technical problems connected with these methods. 1 year ago, it was one article was published that it was theoretical article. They calculated possible yields of actinium, possibility of production. Here you can see the sketch of different targets. Here you can see several converters, 3 converters, and the space between them is for cooling by water stream. And here you can see also for encapsulated radium targets. I don't remember what was the material of this of shells of these capsules, these targets. I think maybe neodymium or something like that should be stable for radiation, and also should be stable for water, hydrogen peroxide, and something like that that may form during the radiation. These are two different total is for converter, but I don't remember what is material and maybe the most interesting radionuclide
that may be produced by photonuclear reaction is the molybdenum-99, because molybdenum-99 is one of the most important medical radionuclides. It's used for technetium generators, as I already said, but it's used for many years for generators. But sometimes we had big problems with shortage of production of uranium. It was due to problems on nuclear facilities, nuclear reactors that produce uranium. Sometimes some accidents or some fuel changing or something like that. And in this time, when the reactor was not in operation, there were no possibilities to produce molybdenum for global market, and sometimes it was really a big problem because millions of patients every day, not every day, but regularly need treatment with this technetium. A number of different different procedures may be demand this technetium. It's not only for cancer treatment, it's also heart diseases or others. And now we have so much nuclear reactors in the world that are suitable for production of radionuclides. And from year to year, number of reactors decreases. Different reasons. One of the most important reasons is nuclear safety, problems with decommissioning. Most of these reactors are too old. There are no plans to build new ones. For instance, in Europe, I think in the United States also, maybe only in China, Korea, and maybe other several countries. They have plans to build new research reactors. And therefore, now we have tendency to replace a nuclear reactor methods of production by accelerator ones. Because accelerator may be easy to operate with accelerator, you have no problems with nuclear safety, no spent fuel, no radioactive waste, and you can switch off beam by very easy. You can switch off, no problems with accelerator. Not like with the reactor, a lot of problems with shutdown, decommissioning, and other issues. And therefore, several methods, accelerator methods, were developed for production of molybdenum, and two of them use gamma rays of high energy that may be obtained in accelerator collectors. The first one is production using enriched molybdenum isotopes, molybdenum-100. But in this case, the specific activity of molybdenum is low, and it is more difficult to produce a common generator for production of technetium. You have some problems with logistics because generator, usually such kind of generators based on liquid extraction, and therefore they will not be radiochemically applied in form of ring. You have some radiochemical facility for production and distribution of technetium. It's not so convenient for medicine. And the other possibility is production by photofusion of uranium. In this case, you can obtain this product with high
activity. Here you can see the reference for one new article that was published in scientific reports that suggested the method of production and separation of molybdenum from irradiated uranium type. And in this case, you need not use enriched uranium like with common method of production of molybdenum. Typical method is irradiation of uranium-235, low enrichment or high enrichment in irradiation in the reaction by thermal nuclides. And this method is very relatively complicated. And also you need enrichment of uranium. In this case, you can use natural or even depleted uranium. It's not a problem for production of uranium. And maybe several years ago, it was the commercial electron accelerator, specially dedicated for radioisotope production, was developed. This is the first model in the world, the first one. I don't know what is the practical experience of application of this accelerator, because it's quite new, and it was published on some websites that that the number of these accelerators were they were bought by North Star Medical Corporation for production of medical radioisotopes, especially for actinium-225. It means that this method that we discussed will be applied in practice in industrial scale. Therefore, I think that nuclear reactions will be very useful for application for radionuclide production. Not for it will be especially important for several radionuclides. Of course, photonuclear reactions cannot replace charged particles, cyclotrons. But in some cases, for instance, in production of molybdenum, scandium, copper, and actinium, this may be a method of choice because of high radioisotope purity, relatively high yield, and in this case, it is preferable. Okay, I think that's all what I prepared for you today, but I think we have used several minutes for discussion. Discussion.
You tried direct production of technetium 99? Have you tried direct production?
No, we don't try the production technetium 99. It was not interesting for us from scientific point of view, because it's in Russia we have large capabilities of production of technetium, and the price of technetium is very low. I don't remember, maybe $1 per curie. I don't know. It's really low, and therefore now in Russia really it's not no demand for development of new methods of technetium production, because we have big reactor facilities in Dimitrov governments, and they routinely produce by them for technetium. We produce other isotopes of technetium. We produced technetium 95. We use this radionuclide as a tracer for development of extra technetium, because it has more convenient half-life, about maybe tens of days. It's much more convenient than work with efficient line with 6 half-life, 99 and 6 hours half-life, extremely low. And chemistry obsession is important, it's very interesting. Development.
I have another question about the expression of the yield.
Yield?
Yes, that expression is only for using photons.
Yes.
That is
What
only
do you
for
mean
photons.
this expression, this one? Yes. This one. No, it's really the same will be for for other methods. But the problem is here. The problem is that it depends of many values. For instance, it depends on you will have different kind of spectrum. For instance, if you have different converter. For instance, if you have thin converter, we will get something like that, for instance. Now, for cyclone, you will have much more intense. And therefore, if you change your experimental condition, you will have another value of your yield, and therefore it's difficult to compare. And the same will be when you use different kind of targets. For charge particles, it's very easy to calculate sigma yield because you have complete accumulation of radiation in your target. But for gamma rays, in many cases, you have penetration. We will have different and also we will have difference when we use small targets and big targets. Therefore, another experiment to compare, in any case we use thin converter and thin target for reaction. In this case, it's possible to condition of experiment looks like more ideal, and it's possible to use compare one experiment with another one. These calculations become more easy. Ask questions. You can also ask questions about our first mark, nuclear reactions. My book produce the Rosatom and rising oxide in regular basis.
Which method do you use to calculate the cross section? To measure cross section?
We usually we calculate the sections in our experiments in charge particle. We measure cross section. We measure them. We measure using we use several foils. Between foils, we place degraders. For instance, we have here 30 MeV protons, for instance. On the first target here, it will be 29, for instance, after first degrader. Here, we or something like that. And then we measure activity after irradiation, we measure activity of each foil, and then using from this activity, it's easy to calculate cross section for each point. For modeling, we use really we don't use special programs. We use already prepare database of cross section with the name of this place is go to 0 to 1. I think. This is the result of calculations of cross section using
That is, yeah, when you measure it, the cross section in the expression, will you calculate the energy? I mean, the energy of the beam you measure it also, or you?
energy of beam. Yes, we measure it, but we have no special type of light or something like that. And therefore, in this stack, we also use several foils, for instance, for titanium, aluminum. It depends on what your particles. We have a number of these molecular foils, and using these molecular foils with small cross sections, well established, we use them to estimate both initial energy and to estimate measure current. It's not so easy, but it's possible. Of course, we measure independently the current, but sometimes it is not so precise. Then when we use this
So in that case, you get the curve of the cross section, and from that, you calculate the yield, right, from the cross section. You calculate the yield of the reaction from the cross section.
I think it's very easy. This is a special free of charge program to calculate from cross section yield.
Yes.
The name of this program is big radiochemical yield or something like that. So it's made by Rosatom in France. It's possible to use it. It's very easy to calculate.
Yes, I'm using your own data, right?
Yes, we use our own data, but sometimes we compare our data with others if they exist. Sometimes we investigate reaction they have no previous data. Of course, it's possible to compare with theoretical modeling, but it's not. Maybe some discrepancies between theory and practice. It's normal. Other questions? There are no questions. Thank you for your attention. Thank you. If someone has any questions, I can also.
we are putting down.
No, tomorrow. Yeah. Cross section, you can make calculated it's possible by Excel, it's not like that.
Yes, they got.
Part of the activity is to make some modification. Second,
And I use one expression that I saw in one. And I sent to regression funds and I said, not give them one that I use in that expression. And they tell me that that's expression. And they send me another expression. And that's like, I agree with that.
and you also have protection of section.
It's with the same. Where we base it also. Then. Yeah. I'm going to use also when we mention the association. And we need to make it.
75 years. 75. I think all this will go.
In the whole world.
Yes, operating, yeah, I think operating is all one. In Russia, it's what the lady second, or says one Russia, but not she. First was definition.
Yeah.
Yes, and now they also produce vertical. I don't know what. Yes, it's now they also produce one of them is
Yes, but what are you using?
really it's low strength. Maybe 54 seconds.
What was the? But how, why they started funding like, and also for easy to and then it's pretty long time. Yeah.
Еще на двоем виде после того, я, к сожалению, не видел, но я представляю, что это будет сказать. Я посмотрю.
But in any case, that is the goal.
Так, все, вот, прекращается. А он что, не успевает доехать, что ли? Ну, мой, вы прикалываетесь? Ну вот, да. Просто я им сказала, что он через 10 минут приедет, а он не ну, давай, понимаешь, что он закрыл, даже Just ничего не буду говорить, да? А,
Да. Добрый день всем. Еще раз.
Да, Владимир.
Я думаю, можем начинать. Hello, everyone. Sorry, I'm not at the building at the moment, but I will be very soon. But we can start with the short presentations. I think Andrei, are you here?
Yeah, I'm here.
Andrei,
Yeah, I'm here.
Andrei.
Владимир. Владимир.
Just a moment.
Да нет. Да. Нету. Ну, сейчас возьму.
Да, давай, а ты где? Давай, хорошо, список. Да, давай. Окей. Телефон, конечно, я же с тобой разговариваю.
Ладно, давай. Давай, пока. So, let's start without Vladimir. Maybe just briefly presentation about yourself, about your hobby, about your scientific work or something. So let's start from Nelson Enrique Villa Pineda. Hi.
Hi, Steve. My name is Nelson Enrique. I call me Nelson or Enrique. I study physics in Venezuela. I'm from Venezuela, from South America. And then I studied nuclear physics in Tomsk Polytechnic University. And now I'm in finishing my PhD program in chemical technology is the name, the official name, but I'm working with production of molybdenum-99 in cyclotrons. I already finished it. I'm just finishing my dissertation now. And what else I can say? Do you have any questions?
Yeah, thank you very much. So, next one, Galibjon Juralievich.
Yes, me. My name is Mehmanov Galibjon. I'm from Uzbekistan. We call me Galib. And nowadays I'm studying Tomsk Research Polytechnic University, Master of Nuclear Medicine, specialty pharmacy, radiopharmaceutical production. So,
So in Tomsk now it's too cold.
yes, Tomsk is cold in Moscow, but
beautiful.
but no, study is very good.
Okay. See. So next one, please, Aliyu Musa.
My name is Aliyu Musa. I'm from Nigeria, and I'm currently studying my master's degree in Tomsk Polytechnic University, studying nuclear physics with a specialty in nuclear medicine. And I'm presently doing my research in the production of a radioisotope. Maybe I want to produce a copper-64.
Yeah, I see. So you're working with Mehman, yeah, in the laboratory.
Here is my research as well.
Okay. Thank you. So next, please, Lutfi Aditya Hans Nova.
Hello, my name is Lutfi Aditya Nova. You can call me Lutfi, and I am PhD student in Tomsk Polytechnic University. I am from Indonesia, and now I am conducting research on production of iodine-123 and its application in vitro and in vivo. I'm working with Professor Mehman.
Yeah. Okay, thank you very much. Amar, please.
Hello,
Introduce yourself.
Omar. I'm graduated from nuclear power plant and operation from Tomsk University, and now study master degree in Tomsk University in nuclear power.
Yeah, okay, good. Thank you. Ekaterina, please.
me or and at the same time, I'd like to student here at the program of internet master of radiopharmaceuticals, that's why I'm here.
Alexander, floor is yours.
My name is Alexander. I'm from Belarus. I graduated, first I graduated in Belarusian State University, then I graduated master program in St. Petersburg State University, specialization in radiochemistry, and I have been working since 2013 in
In which
institute scientific institution and the joint institute of energetic and power the official the name of institute.
Okay. Next one is Anastasia Bogdanova.
Steve?
Okay.
You? My name is Anastasia Bogdanova, Anastasia, or Nastya for short. And I'm a student of a master program in chemistry at the National Academy of Science, Belarus. I'm from Belarus, and also I work as an engineer research in the research institute of nuclear problem BSU means in the sector of biophysics research. And there I investigate biocompatibility of carbon nanomaterials, especially graphene quantum dots and boron nitride quantum dots that are both used for diagnostics of cancer, and especially boron nitride quantum dots is a new career of Rosatom that can be used in boron capture neutron therapy. That's all.
Thank you very much. Thank you very much. So next one is Anton Zverev.
Hello. My name is Anton, and I'm from Belarus, but I'm born in from Minsk, but I was born in London. It's another region. It's sometimes called Chernobyl region.
What is that? Why it's called Chernobyl? I mean, it's called Chernobyl.
Yeah.
Uh-huh.
So I'm a student of bachelor degree now. And maybe it's all. For the time, I have research work with Benton reagent at batch 7 and 4 for transformation of methanol and determine the products of this transformation.
Thank you very much, Anton. Albina Irina, the floor is yours.
My name is Nikita, and I'm my specialty is high energy chemistry.
Radiochemistry.
I was for the public sector of tomography, and this experience signifies my experience in radiopharmaceuticals.
Perfect, thank you. So next, Liana Belmont.
My name is Liana. I'm 22 years old. I'm from Belarus, and I'm finishing process integration this year. My major is chemistry of energy, and I wanna try my future with pharmaceuticals, and I'm really glad to be here now.
Thank you very much. Thank you very much, Liana. So Vladislav Yermak, floor is yours.
Just one.
I'm also from this unit, we like, many of us studying the same group from chemistry. And as we're both know, I was born in London, it's a town of Leeds. And also I'm a final year student, so I don't have much work. One time I've been researching the influence of essential background of radiation on amount of like amount of harm things involved.
Oh. Okay. Okay, thank you very much. So, Nastasia Vertinskaya.
Good evening. My name is Nastasia Vertinskaya, nice to be short. My last term, I'm 6th-year student of high energy chemistry of the Belarusian State University. My last term paper was related to the effect of was related to the study of the effects of radiosensitizers on fats. At the beginning of this academic year, I had an internship in positron emission tomography center of the Republic of Belarus, and I want to connect my life with radiopharmaceuticals and be useful for people in this sphere. I'm glad that I can improve my qualification abroad, and so I believe that this school helps me to become a highly qualified specialist.
Good. Okay, thank you very much. So, Basim, the floor is yours. Hello.
Well, I'm Dr. Basim from Iraq. University is Kufa University. My field is laboratory radioactivity. Also, we can say about radiation protection. Have many specialization of the fields, for example, biosensor for to detect for radon gas. Also, I have many articles about nano particles. I want to complete some research about to use medicine with nanoparticles. My relative from Malaysia, and I'm very happy to join this event also. Yeah, thanks.
Thank you. Thank you very much. So, next one is Elizaveta Lev.
Hello, Lisa. I'm from Belarus, Minsk, and since 2018, I have studied at Belarusian State University. My specialty is radiochemistry. So my last term paper is related to radiation chemical transformation of alcohols in diuretic aqueous solutions. So this group is a simple model that can help us to understand different processes in other complex systems. So it's really interesting stuff. Also, there are only 2 laboratories of isotopic productions and 2 laboratories of nuclear medicine in Belarus. So it's very important to adopt the experience and knowledge from our foreign colleagues. So I'm very happy to be there. Thank you.
Okay, thank you very much. So next one is Alexandra Zhardetskaya.
Next, there are reagents. University with degree in future lab chemistry, and there is pharmaceutical. And I think this space is an opportunity to get knowledge in this area and look at our skills which we receive before. Thank you.
Sure, thank you. Next one will be Олеся Baranova.
Energy chemistry, vision of chemistry. So that is require large particles in medicine, for example, magnetic resonance imaging or targeted drug. And I would like to thank the opponents for the opportunity to learn more about radiopharmaceuticals and maybe apply this knowledge in my further research.
So, and next one is Margarita Borshevskaya.
And the department is I going forward to involve my knowledge of nuclear medicine, radiochemistry, and I think it's like my work, so
Thank you, Rita. Next one is Igor Russo.
Nice to meet everyone. My name is Igor Russo. I'm the fifth year student of the University Chemical faculty. In my free time, I do a lot of events in our university. I'm a head of Creative Union, and also 6 months ago, I did research work about that radiation alone, and nice to meet you. I'm very glad to be here. That's all.
Thank you. Perfect. Thank you very much. So, Ivan Dekan, the floor is yours.
Hi everyone, my name is Ivan Dekan. I'm from Belarus State University. I'm also a chemist from the specialty as high energy chemist. My last term paper was conducted with National Data Alone, which was work on strontium-19 and yttrium-19, and also what I can say about that. Also, I think I will continue to work in Belarusian State University of Meteorology with this national accolade, and will improve my knowledge and skills with chemistry, reaction physics, and all sciences between all this.
Okay, thank you very much. So, Riam Nasser, the floor is yours.
I'm Riam Nasser. I'm from Egypt. I'm graduate from Faculty of Science, and now I'm working as a researcher at the National Institute of Chemistry and Physics. And I had my PhD in 2021. I think it's great that Jennifer will join this winter school because
I know more about the radiochemistry. I'm now thinking to some new way to line up next research.
Thank you very much. So, Mohammed, the floor is yours.
Hello, everyone. I am from Egypt. I'm studying the PhD at the University in Gothenburg. Russian. I'm now working postgraduate in the university, and that's why I'm working in Egypt in scientific research at the Radiopharmaceuticals research. I am attending my dissertation in PhD at the university. My interest is radiation prediction, radioactivity, especially when we work with techniques to detect the radioactivity in the mass samples from the
Thank you.
And it's the third time in this school, and I'm very happy to be here with Ray and other.
Thank you. So, Daria Frolova, the floor is yours.
Medical literature is very interesting and informative to me, and I started I think it's with people with serious illnesses, and I try to gain knowledge to help them. Also, I know French people.
Thank you very much, Daria. And next one is Olga Urbanovich. Yeah, also.
I'm Olga. I'm studying University of Cambridge department. I'm here because I was chosen for my department to supervise and scholarly students. So right where I'm here, but also this school is very useful for me because my research is quite connected with radiation, because I study radiation transformations of hydrogen-containing substances such as alpha gas, because they are simple models for lipids. So this is my research work. And I'm happy to be here, and I thank our organizing committee for the opportunity for me and for our students to be here to visit such events. And I think that I believe that it will be very useful for us to engage our international committees.
Thank you very much. So, and last but not least is Vladimir Petrov. Not Vladimir Petrov. So, but Mikhail Ostapenko. Mikhail Ostapenko. No, Vladimir Petrov. Let's start.
Yeah, my name is Vladimir Petrov. I'm a professor here in the radiochemistry division of our chemistry department, and I am one of the organizers, not me. Organizer is Andrei, which I think, but I hope that this school will be successful and you will learn something new. As I understood from the Zoom, I was connected. Many of you either working with radiopharmaceuticals or working with radiochemistry, but I'm quite sure that something will be very new and very useful for you. I hope so, and yeah.
So
welcome.
Thank you very much. Yeah.
Yeah. And
let's go to the restaurant. Maybe.
Right now,
yeah, we can. I think. Let's go.